Hello, everyone. This is Chen Peng from San Diego, California. I will take this opportunity to give you a brief training session on NMR prediction using Mnova software tools. In this training series, we have already done the SMA 3D structure using stereo feeder, NMR, chemistry perturbation using M-binding, the electronic lab notebook using M-book, the automation workflow using MyGears, and today is the prediction of NMR for molecular structures. And in the coming few days, we're also going to have the NMR and MS for structure confirmation, verify, knowledge base, database for analytical data, spectral databases, ligand protein binding screening using NMR. That's our screen. And we are also going to have two newly announced ones in May. That's the tips and tricks using Mnova. And the process, analyze, and report your LCMS and GCMS. That's Mnova MS. We are going to have more to announce as well. Yeah, please. We're going to send you the slides, I believe, or the email notification, so you can register or view the past presentations. Okay. The objective today is to introduce you to the Mnova NMR Predict plugin as a set of tools for predicting proton, carbon, and HSQC spectrum from an organic chemical structure, and using them to assist your routine NMR analysis. We will give you understanding of the advantages and the unique features of this NMR Predict plugin. And we're going to give you the tools to evaluate the software by following our basic demo of the software. Yeah, I will try to slow down my pace, especially compared to Monday, the Monday one. Yeah, so you can follow my demo today. Right, so as you know, over the years, Matrix Lab Research has developed a lot of products, including the basic ones for NMR, LCMS, GCMS, and IRUV with Raman data analysis, processing, reporting, etc. On top of that, we have a list of advanced plugins like database, UPAC naming, NMR Predict, which we're going to focus today, QNMR, structure elucidation, verify, and the specialist products like binding, biologics, high order structure, physiochemical property prediction, reaction monitoring, screen for ligand protein, FB fragment-based drug discovery, simple mixture analysis for targeted quantitation, stereo feeder for 3D structure determination, etc. Right. So yes, today we're going to focus on here. Just a reminder, NMR Predict is one of the plugins in Mnova, and if you have the proper license, you should be able to see this prediction ribbon in this modern graphic user interface. Okay, the following demo, we're going to use this interface instead of the classic old interface, right? So if you are still using the old one, yeah, please go to Edit, Preferences, General, Interface, and set theme, the theme to modern. Then you restart Mnova, right? Then you will see this, we call it modern theme. Yeah, the ribbon-based user interface. Okay, so what is Mnova NMR Predict? It is a set of tools in Mnova that predict and draw the NMR spectrum from an organic chemical structure, which can be used as a guidance for manual or automatic interpretation of your experimental NMR spectrum. Right. It predicts proton, boron, carbon, nitrogen, oxygen, fluorine, silicon, and phosphorus chemical shifts. Right. It also predicts the proton to proton J coupling constants, proton to fluorine, and carbon to fluorine coupling constants as well. Right. So chemical shifts and some couplings. And Mnova draws the it synthesizes the predict proton chemical shifts spectrum, proton NMR spectrum, using a 4 quantum mechanics approach. Yeah, with a higher order effects and strong couplings considered for spin systems of any size. Yeah, this is very important. Yeah, we do the high order effects and strong couplings in the synthesized spectrum, and it's not limited to the size of the spin systems. Yeah. That's why the produced spectrum looks very realistic. Mnova NMR predict also includes a spin simulation tool. Right, you can enter your user-defined spin systems and like the proton, the spin chemical shifts and J couplings and which kind of spins you have. Right, then Mnova will synthesize the spectrum, taking into account the strong coupling effects and high orders. Right. For example, if you define the X system, it will simulate the spectrum. And if you want to change the chemical shifts, yeah, you can just click and drag and move the peak closer to the other one. Then you will see in real time the roofing effects like that. And if you move them close enough, then you will see strong couplings. What's the algorithms and the database behind this plugin? This is a very common asked question. So if you go to the option of Mnova predict, for any of those predictions, you will see there are two common options there. One is Mesh Lab predictor, the other one is Multigraph NMR predict desktop. Those two are the common ones, and if you have the license, both are available for you. Okay, so for carbon-13 chemical shift prediction, Mesh Lab predictor is developed by our company using several machine learning algorithms on large databases. And the Multigraph NMR predict desktop is developed by Multigraph and Professor Wolfgang Robin using the neural network method trained by such a big collection of verified carbon-13 spectra, right? And there are two different engines there. One is the host code-based, code-based approach. The other one is a neural network algorithms trained for subset of those compounds, right? So it's a combination of both engines there for carbon-13 chemical prediction. For proton, it's similar. It has our own Mesh Lab predictor and the Multigraph predictor. Yeah, here is slightly different. It actually also have the algorithm from Professor Precht from ETH Zurich, right? All of these consider different solvents as well. For other nuclei, it's based on the Hosey code approach, yeah, from databases, right? And remember, you can also train the prediction using your own assigned chemical structures. I also want to mention that the prediction of the J coupling constants have been significantly improved by our Mesh Lab predictor in the recent years, right? For example, for the prediction of the carbon to fluorine couplings, we created a machine learning prediction model, which was trained using a large data set of experimental values with more than 20,000 assigned carbon fluorine values, taken from the literature. Yeah, and we did a similar work for the proton and the proton fluorine J carbon constant predictions. Right. So if you have a structure, you do the prediction. For example, in this case, a carbon 13 NMR prediction, you will see the couplings from fluorine to the carbons, like here for this carbon, right? And in the prediction table, you will see the couplings from proton to carbon and fluorine to carbon. Yeah, of course, by default we suppress the couplings to proton because we assume it's a proton decoupled spectrum. Yeah, but you have the option to turn that off as well, right? And this is the other one here. The prediction also has the smaller couplings from the fluorine here as well, and you can see that in the table. Right. So what can we achieve today with the right? So from this training session, I hope you will get familiar with the tools for NMR prediction. I'm going to show you how to use the predict spectrum to assist the peak assignment of experimental NMR, and how to use the predict spectrum to help distinguish region isomers, and how to improve the prediction by training the predictor. And finally, I'll show you how to use the spin simulation to simulate spin systems, which is good for learning and teaching NMR. Right. I hope you're ready for the training now. Right. Again, please make sure you are using the new modern theme for the user interface. So you can see these ribbon-based tools. If not, yeah, choose from the edit preferences, set the modern theme, and restart Mnova. Okay, everybody, hope you started Mnova as well. Hope you can see my screen, and the refreshing of the screen is big enough and fast enough. Yeah, this is a typical interface of Mnova. It's similar to PowerPoint, and on the left-hand side, I typically have this pages view. So I can know how many spectrum or spectra I have within the current document. If you don't see this, yeah, make sure you go to View and take this for view, or no, take these pages. Okay, yeah. For example, if you don't see that, then you tick that, then you will have these pages. Yeah, you can dock it to here. Look at that blue shade. Yeah, that's where it's going to go to. I make it as small as possible. And then I also have this data browser. Okay, if you don't see it, or if it is hidden here, yeah, you can change from the tab here to make sure you have the data browser. If you don't see it even here or on the right hand side, then go to View, click data browser. Right, so you have data browser checked, then it should be somewhere, and I prefer to put on this side. This is just like the convention of PowerPoint. Right, so here I already added the folder where I have the data sets. Sample data set I'm going to use today. Yeah, if you already have it on somewhere on your desktop, for example, you can open from there directly if you're used to it, or you can click here. I hope you can see it. I hope it's not blocked by your webinar panel. Yeah. So here there is a add location. You click that. You navigate to where the data is, like what I have here. Yeah, you choose that folder. Yeah, then you put the name, like what I put here. Right, then click OK. Then you will see that folder here. Right, you expand it, then you see the, yeah, that's it, fluorocinamic and brucine, and then the Viagra, NMR. Yeah, there should be 3 folders. Yeah, if you don't have it, yeah, maybe you want to have some structures by yourself, okay? Some NMR spectrum, because that's what I'm going to show you. Okay, hope you already have the data ready. I'm going to slow down, tell myself to slow down. Right, hope you're following with me. Right, so the first one I'm going to show you is I'm going to have a molecule, this fluorocinamic more file I gave you. Yeah, so I drag to here, then I have a structure. Okay, if you don't have it, doesn't matter, go to the molecule ribbon here and draw structure. Okay, go to the draw, and this is the rinse. Do a quick work like this. Then you draw the chain, right? 1, 2, 3, 4, and click here. Add a double bond. Hover on it. Click all oxygen here, another oxygen, and here click 1 time, and F. Then you have the structure. Very, very fast. Okay. Click escape to escape from the structure sketching mode, right? So you could either draw the structure or you can import from the more file, as I showed you, right? So now I have the structure, and in this molecule ribbon, make sure you have this compound table open, right? See, I drew it and I removed it, but it's still remembered in this compound list. So I have to delete it from here. I don't need 2 structures, 2 redundant ones here. I only need 1. And once you have the compound table showing this structure, you can see there's some basic properties here, right, which should be useful for you. And if this is too small for you, remember to use those little handlers to change the size, right? Make sure it is visible for you, because we're going to use this one to visualize the structure, especially when we have multiple pages here. Okay, right, so we have a structure, and now we're going to do the prediction, right? Remember, the predict ribbon is like this. Okay, we have the proton prediction, carbon, and those other nuclei where you can expand from here, right? And next to the prediction button, there's always like a table to show the prediction values, and there is a setting. Like here, if you click on it, you see which engines you're using, and the details for every predictor. And also there's some more here to show some parameters you want to use, like strength of the field you want to predict with, the range of the spectrum, how many data points, and line width, what solvents you are using, okay, and label protons you want to include or not, right? Remember, this value and this value will be automatically adjusted if you are using predict and compare, which we're going to show you if you are experimental, okay, right? But here, yeah, if you just have a structure, you can use some of those, change some of those parameters by yourself. And actually, you don't even need to come to here. If you right click on the structure, you will see the options for you to predict proton, carbon, HSQC, and the X nuclei spectrum. Okay. Now, so let's predict a proton using the default parameters. So I get the proton spectrum here. And if I right click on here, or I can even just right click on here, right? I can choose carbon-30 inspection. Then I get a predict carbon spectrum in a new page, right? So now you have two pages. From pages view, you can see that's proton, this is carbon. And you can see the interaction. If you hover your cursor on the atom numbers, you will see the highlight here, and vice versa, right? And now I right click here, I want to see HSQC, right? So it's going to show like a one bond correlation spectrum between the proton and the carbon, right? So this is the HSQC. Yeah, you can attach the predict proton and the carbon to here, right? So you see the 2D. Yeah, if you want the why this color, what are those lines? That's the correlation, yeah, between one the proton and the one the carbon. Yeah, the color can be changed. Right click, properties, and the assignment. See, I changed it from the default because I didn't like the brown lines there. Okay. But HSQC, and here I want to show fluorine. Yeah, there is a option for fluorine spectrum as well. Right. So you get a fluorine spectrum. I can zoom in and see the details. Okay, so that's the proton, carbon, HSQC, fluorine spectrum prediction from our structure. Right. I hope you followed with me for this prediction using a structure. Right. So next, I'm going to create a new document because I'm going to use the new molecule. Okay. So I go to File, New. Now I have a new document, blank one here. The old one is still there. It's kept. Everything is there. You can save that, or you can just close it without saving. So I have a new document here. Are you guys ready? And I go to the data browser. I'm going to use the exciting molecule, especially for this boring time, the Viagra. I'm going to open the molecule. Yeah, that's the Viagra.morph, if you have it. Yeah, we also have a few other region isomers there. Okay, so I open the correct structure of Viagra. I also have a proton and HSQC spectrum there. Right, so I will open the proton spectrum. Right, this is experimental. Okay, you can see by default it's not doing the baseline correction. So I will just go to the processing, quickly correct the baseline. Okay. Right. So now if we're going to analyze a spectrum like this, and we want to understand whether this spectrum is compatible with this proposed structure, what should we do? We typically, first of all, we pick the picks with the multiple analysis, right? Okay. So we go to analysis. We just quickly do a automatic multiple analysis. Remember, for this NMR analysis, we need to NMR license, Mnova NMR license. Yeah, otherwise, you won't be able to open the experimental. Although you can still do prediction if you have only NMR predict license. Okay. So now I have the experimental spectrum analyzed with picking, multiple analysis, and integration. You can see that. Yeah, I can zoom in to take a closer look. For example, here. Yeah, apparently this is like two very close multiplets taken as one. Yeah, so I can just hover the cursor here, click and drag, and split it. Right. So I know this one is another one, right? For spectrum, and the other one seems to be okay. Yeah, apparently this methyl group, CH2, and another methyl group, and solvent is recognized. So it's a water peak recognized. Yeah. Some impurities there. Okay, so quick analysis. And now we want to confirm all those peaks correspond to some of those protons there, right? So there's a very nice tool here in prediction ribbon. We have this predict and compare, and predict and highlight. Right? Basically, predict and highlight, if you click on it and you click this predict, it's going to predict a proton spectrum using the same NMR field strength and the same solvent, which you can see from the parameters table. Yeah, if you don't have parameters table, go to view, turn on these parameters. Yeah, you will see that table. I also docked it to here. Right. So it's going to use the same solvent, which is DMSO, and this is 500 megahertz. Yeah, so it's going to use those parameters and predict a spectrum. But remember, it doesn't show it. It only highlights it, right? So that's predict and highlight. Now, if you move your cursor on any of those protons, you will see the highlight of the chemical range, the range and the center, right? So that's useful if you don't want to show a predict spectrum, but only highlight the range and the chemical shift center, right? Of course, sometimes we do want to see a spectrum, so I just click predict and compare. It does the same thing, but it's going to show the predict spectrum here on the top. Yeah, this is the predict, and this is the experimental, right? And if you now, if we want to use the predict spectrum to help us do the assignment, I think we can easily do that, right? Right. So remember, we have an assignment ribbon where there's manual assignment and automatic assignment, right? So in this class, I'm going to show you manual assignment only. Okay. Automatic assignment works as well, but yeah, manual assignment is much more fun to do it, especially you have a predictor. It can help you to understand, to characterize the NMR and the structure, right? So in this case, I'm going to follow each peak and see what I can do the assignment. Right. So here's 25, this close to it, and the line shape looks similar. So I will just highlight the experimental, click here, or the shortcut key, that's A. Okay, I click this multiple label, and again, let's look at the structure here. We can look at here, 25, right, it is here, right. So yeah, it's assigned, the color shows the confidence judged by Mnova, right? Or you can use the compound table to do that as well, right? So either way, from here or from here, right? So the next one, I have this doublet to the next, right? And this doublet to the right. So that one apparently is 11, right? So I just click 11 here. And the other one, DD, doublet, was close to 16, right? So I will put it here. And this one, 15, I'll send like this way. And I want to move to the other side. You can click and drag using here, or you can show this full view. Okay, it will show where you are, so you can move from around there, right? So now I'm looking around those peaks. So here the prediction has a quartet and a singlet, right? You can see the prediction is not exactly the same as the experimental, but here, move that away. We know there's a 18 and 33 there. So 18 is CH2, right? So it should be that quartet, right? Because it's next to this CH3. And the singlet corresponds to 33, which is here. And that should be a methyl group. And you look at here is 3. Integral is close to 3, right? So we're quite sure which is which. So I click here, the quartet. Make sure I click the quartet. Let me, yeah. And then I click here, 18. Right. This one, the singlet methyl group, which should be 18. No, should be 33. This methyl group, right? So I did that. Yeah, I can carry on. Here it's like a very small singlet, 0.44. Yeah, I think we can ignore that because this seems to be an impurity, right? So here there is a triplet, 1 and 6, right? So we know it's one of those. So I just click one of them. Yeah, Mnova knows is a symmetrical CH2, so it assigns both to the same peak here. And this one, 30, right? So it's here, right? And that's the DMSO. We ignore that. This triplet corresponds to 5 and 3 here. And then we have this 7 for this singlet. It's a methyl group, which is here. Right. Quite clear. Move around to the other side. We're almost done. Here, K29. Which is here, right? And the 17, this one is 17, right? It should highlight on the structure, which is here, right? And the other one, the last one, 31. Yeah, you can see with the help of the 1D NMR prediction, we were able to assign almost all of the protons here. And of course, this is when we have a very good prediction. In the real world, sometimes if the structure is novel, then you may not be able to be so lucky and you may not be able to assign everyone. Yeah, but at least you can have some started, then you can use the 2D NMR, right? So that's the assignment using that. And yeah, if we open the HSQC as well, right? So let me go to the data browser. This HSQC here, remember, I do that. You can see the assignment comes to here. It's all displayed on here as well, right? And actually, if I had this displayed before I did the assignment, the HSQC peak will be automatically assigned, right? So in this case, of course, we know which is which, right? It's quite easy to tell the carbons, right? We don't have a carbon spectrum here, but we can assign on here. For example, yeah, we know this guy is 11, so it must be assigned to carbon 11 as well. Right, so let's go to structure compound here. That's 11, right? So it should be there. So we get the proton and carbon assigned. And so it's here, we just click on it, and it should go to the, let me check, 16, right? So let's put on the 16 here. Right, so 16 and 16, right? And so it's here, 15. Yeah, you can carry on. Right, so I will not repeat that, but just let you know, proton, carbon can all be assigned in this way using the different spectrum within the prediction as well, right? So next, I'm going to show you how in practice, you can use the HSQC to do a simple predict and verify. Okay, I'm opening a new document. Go to file new, do that, yeah. And then I'm going to open the structure, and I will open the HSQC, right? So I assume I have 2D HSQC and a structure. Then can I use some of the prediction tools to tell me if this structure is relatively reliable, compatible, based on the prediction of both proton and carbon directly? Yes. So if I go to prediction ribbon here, you can see there's a predict and a verify only for HSQC, right? So if you click there, you see there's HSQC option there. Yeah, if you choose that, it's going to draw the rectangles showing the range of each HSQC peak from the structure. And you will color those rectangles based on whether there is experimental peak picked within that rectangle. Okay, so again, you can see, yeah, here, let's zoom into the aromatic region around here. Yeah, for one of them, yeah, for this CH11, you see the range and the highlight on the axis. That's this boxes, right? And there is a experimental peak inside it. That's why it's called green. So it's a grid. And if you go to the other one here, yeah, that's the next one. And this one, 16, yeah, it's this one, right? And so are the other ones, right? You can verify that, right? So you can see all of those boxes are green because there's an experimental peak picked within it. So I would say this gives you a simple verification confirmation that this structure is probably compatible with the available HSQC here. Right. And now, if we want to have an isomer, region isomer of this, okay, I'm not going to use those molecules because I realized, there's some display problems with them. Okay, so I'm going to just simply, let's change the molecule here. Okay, it's quite easy to do that in this molecule ribbon. Right, so I use the delete tool. So suppose I want to delete that bond. Okay, I'm going to connect this CH3 and the CH2 to here to make a region isomer. Oh no, yeah, if I did something wrong, I just click escape here. I should use that one to connect the bond here. Right. So this is still the same element composition. By the way, I can move an atom using that move. Right. Okay, this is still the same element composition. You can look at the molecular formula and the molecular weight, but it's just a region isomer because it's connected here, right? So if with the structure like that, if I use the predict and predict verify, let's see what we get. Right, so from here you can see there are two rectangles that don't have a experimental peak within them. So they are displayed in yellow as a warning, right? You can see they correspond to 31 here and 30, actually this one, method group, right? So this gives you a rough idea that this structure is not so compatible with the HSQC, and the reason is those expected regions are not matching the experimental observation, right? And of course, we can try different ones. For example, if I go to molecule, I will remove another one. Yeah, actually, I have another molecule isomer included, right? But since the time is getting close, yeah, I'd rather skip that one. Okay, so this gives you an idea. You can have region isomers and compare with your HSQC and give an idea of like a rough ranking of which one is more compatible. Yeah, next I'm going to open the another document. I'm going to open the last data set here. Yeah, for the last data set, brucine, I have this molecule. I have proton, carbon, and HSQC, right? So in this case, I'm going to show you that let's open the carbon spectrum, and we have this molecule. Oh no, that's the wrong molecule. I should bring the brucine, which is here. Right, and if we do a predict and a compare, just a quick baseline correction optionally. Right, so go to prediction here. If we do a predict and compare of the carbon, I hope you are following with me. Yeah, right. So we're going to get the predict spectrum. Yeah, if we zoom in, you can see how what the prediction is. Yeah, there's some differences around there. And if I move to the other regions, right, especially around here, we do have some quite significant differences, especially like here. Move the structure away. You can see 29, 26. Okay, the prediction are quite different. Here, this should be 6 and 3. Yeah, they're also different. They're getting almost together. Yeah. So this will make it hard for us to do assignment, right? And there's some other regions as well, right? So what I'm going to show here is if I already did an assignment of the whole structure, yeah, using proton, carbon, HSQC, HMBC, etc., as I have here, right? This is one I already included in the data set for you, right? You can see I did a manual assignment of every atom, proton, carbon, HSQC, right? HMBC, that's COSI. This next one is HMBC, etc. Right? Yeah, this is very nice. You can do this in Mnova manually, and you will enjoy a lot of solving the jigsaw puzzle, right? And some of those are distinguished of the closed carbons can only be achieved by looking at the HMBC when you can see the key correlations are there, then you can distinguish that. Yeah. Anyway, so I have the assignment of the carbons and the protons for every atom, right? So then I can use that to train the prediction model, the predictors, right? So you can see here there is some tools there for browsing and just searching what your user prediction database. Okay, that's what you normally use. You put into predictor, right? So to do that, yeah, I just highlight structure with assignment. I right click, then there is option showing update proton and update carbon, or even other nuclei, right? If you have the assignment there, right? So in this case, I'm going to only show the update in the carbon-13 prediction using this assignment. So I choose that. Yeah, it's going to show you what you have here. This is the structure, and these are the assignments. Yeah, you can delete some of them to use only part of the assignment for the training. Okay, And I'm going to use all of them. I'll put my name. This is important because in the future you might want to search who put something there. Yeah, compound name, whatever you can put there, the solvent, etc. All those information you can add. Then just click OK. It's going to be added into the predictor, right? And to verify that, you can go to the browse here. Yeah, let's wait a little bit. It's probably still doing that, right? And go to the carbon 13, click OK. Yeah, you will see what molecules were there for the training. Yeah, I have 3. That's the one I just added with my name there, right? Yeah, there's another quinine and the simple molecule like that. And you can delete from here, okay? Yeah, if you don't want to, or if you put the wrong molecule, then you can delete from by using the browse, or you can search by structure, right? Okay, so now I already trained my predictor using this assignment and the structure. And now if I go back to the previous document with the prediction there, and I do another predict and compare, it's going to add to the stack a new prediction on the top. Right. And we can verify that. Yeah, so now if we look here, you can see the top one is in much better alignment with experimental, right? Although it's not totally the same, okay? It's still a weighted way of doing the prediction. Yeah, I mean, it's a weighted of combination of the previous database and your new data, right? You can see here, right? It's not exactly the same, right? But the prediction definitely is much better than the prediction without the training, right? Okay, so that's the prediction with the training. Now, the last thing I want to show you very quickly. Sorry, I'm running a little bit out of time, but I guess, yeah, it's still, I'll still keep it within 1 hour. There's a spin simulation here, as you can see. Right, so let me open a new document. Right, you can see I already have quite many documents here. I go to prediction. I click here to pop up this spin simulation panel. Okay, I can again dock to here or let it float in somewhere. Right, by default, there are 2 spins there, half spin with 1 proton for each. Right, so today I'm going to manually define a ABX system. So the A will be a spin, half spin at 3.2 ppm. Okay, B will be 3.3, close to the first one. I'm going to add another member. Yeah, you just increase from here. Yeah, so you will see, just in case I'm not blocked by your panel. Yeah, I'm going to put X as a bit farther away, 4.3. Right, and I'm going to change this as X. Yeah, just click here. So it's going to be updated here as well. Yeah, you have to click here to see that updated here for J couplings. Right. So for J couplings between A and B, I assume it's like methylene. So it's going to be big. Let's say it's 10 hertz. And between A and X, there's one that's a little big, like 8 hertz. And between B and X, maybe a little bit smaller. Let's say 3 hertz. Right. So we define the spin system. Before we simulate the spectrum, let's make sure we are looking at a certain strength of the field. Let's say 300. Right. And the width, let's say from 0 to 10 is good enough. ppm. Right. And line width, a little bit wider. Let's say 0.7 or 0.8. Right. So now we are ready for the simulation. Just click here, new simulation. Then we get a similar spectrum for that ABX spin system. You can zoom in and see. This is a very typical AV system with a roofing effect, and the X here tiny little bit like that, right? And yeah, if you want to make the camera shift even closer, yeah, you can click here and drag it towards B. You can see this. The high order effect is getting more obvious, right? Or you can get a totally strong coupled peak like that. Right. When you did that, you can see the camera shift changing. And if you want to change the decouplings, just come here, put to something different, and this is all changed. That's why we call it like a full quantum mechanics simulation with a high order strong coupling considered when we simulate the spectrum, right? And of course, if you want to show the students how the difference between such spectrum and the 60 megahertz, right? You just change that and do a new simulation. You get a 60 megahertz spectrum, and you can stack that by dragging that to here. Right. So were you able to follow me? I can teach students on the difference between 300 megahertz and 600 megahertz. Right. So here, even if you can see, yeah, that's the difference. With 60 hertz, 6 megahertz, yeah, you still get the strong couplings like that on 60, but on 300, yeah, they are much better to analyze with much less strong couplings there. I think I've covered every topic that I wanted to follow. I wanted you to follow. I wanted to demo. Yeah. So I hope you were able to follow with me. And there is a last slide I want to show you before we start the polling and the question answering session. Right. So I hope I've convinced you today that NMR Predict provides you fast and accurate prediction of NMR spectra for up to 8 kinds of nuclei. And when coupled with NMR processing analysis tools, it helps you to assign the peaks to atoms and confirm the proposed structures. Yeah, it's a very good tools for interpreting NMR. And also the prediction and spin simulation tools of different fields are very good tools for teaching and understanding, learning NMR. So it's good tools for teaching and learning. Thank you very much. Yeah, I think it's about time to do the poll.